to the... Yeah. Okay, excellent. So now I push play again.
Perfect. All right.
Okay, so we solved the problem. Okay, thank you very much. Okay, sorry for this small technical problem, and I'm extremely happy that you invited me for this occasion, and I'm really happy to join this event. And I should also say I would be very happy to take questions also during the talk. I mean, I don't know most of you, so and you know, it would be extremely helpful if you ask questions already during the talk. I guess there's this hand raising possibility in Zoom, and maybe you can use that, and then Frau Tolz can tell me when this happens. Okay. All right, so as was announced at the beginning, I'm going to talk about this topic of relating seemingly unrelated concepts in physics, which are black holes and quantum computers. Maybe before I go on, I should say the background picture here you can see is the castle in Würzburg, next to the River Main. So Würzburg is a small university town about 200 kilometers to the northwest of Munich. Good. All right. So just to introduce the topic, I think most of you are familiar with the concept of a quantum computer. So a quantum computer is a device which actually processes qubits rather than classical information, and in this way is much faster than a standard classical computer. So at least this is the theoretical idea, and you know, because I'm a theorist, I will continue to think about this very theoretical idea of a quantum computer. Then, on the other hand, I'm going to tell you quite a few things about black holes. So black holes are particular solutions of Einstein's equations. And okay, so there's a lot of excitement about them right now because they have been discovered in the sky in the universe not very long ago. And also this year's Nobel Prize was actually about black holes. And so then obviously quantum computers are about quantum mechanics and black holes are about general theory of relativity. So at first, these things seem to be completely unrelated. And so one of the main messages of my talk is going to be that actually these two concepts have much stronger relations than first expected. And mostly this is due to the fact that, of course, in processing qubits, what is very important is to study the entanglement, or you have to have an entangled state to actually start with something interesting in view of quantum computing, and entanglement is actually a concept that is, on the other hand, related to geometric concepts and of differential geometry. And and this is actually the more precise term in which to relate these quantum computers with black holes. Okay, so let me give you a brief overview what I'm going to talk about in the next short hour. So to bring us everybody to the same page, so I expect everybody of you has a background in quantum mechanics. I'll just very briefly review the essential concepts of quantum information theory and in particular entanglement. And then on the other hand, I think that most of you are probably not so familiar with black holes. Well, of course I don't know, but I assume this might be the case. So let me tell you very briefly about what exactly a black hole is in general relativity. Okay, then the third topic I'm going to introduce is so-called gauge gravity duality. So this is my area of research. So gauge comes from quantum field theory, so a gauge theory in quantum field theory. And gauge gravity duality is a particular map by which you can map a quantum field theory to a gravity theory. And this is actually what is behind this idea of mapping entanglement to geometry, as I'm going to explain. Then the fourth point will be to relate what I advertised in my introductory slide. So I'm going to relate entanglement and geometry. And in this, I'm going to talk about a number of important concepts: entanglement entropy, computational complexity, and the so-called ER is equal to EPR hypothesis. So ER stands for Einstein-Rosen and EPR stands for Einstein-Podolsky-Rosen. So Einstein-Rosen is a paper about wormholes and Einstein-Podolsky-Rosen is a paper about entangled states. And there's this exciting hypothesis that these two things are actually the same. And so time permitting at the end, I'm also going to tell you some related work about applying gauge gravity duality in the context of condensed matter physics. And we had just a recent paper with it. So I'm a member of this excellence cluster CTQ-MAT here in Würzburg together with Dresden. So we are an excellence cluster with 2 different hubs. And within this cluster, we had this recent work. So I thought that would be something nice to conclude the talk at the end. Okay, so let's start with point number 1, and let me briefly remind you what entanglement is. So first of all, here you see a pure state vector. Sorry, I have to. And on the right-hand side, you see a mixed state, which is given by a density matrix. So the state vector is a vector in a Hilbert space. And the density matrix then is written as shown in the top right-hand corner of the slide. And then in quantum mechanics, of course, there's this competition, or I should say these 2 important concepts of an entangled state, which you see on the left, and the product state, which you see on the right. And of course, entangled states are very proper to quantum mechanics. And so an important concept to measure the degree of entanglement is the so-called von Neumann entropy, which is written there. So it's minus trace rho log rho, where rho is the density matrix defined above. And this gives us information about the degree of entanglement of a system. In particular, it's maximized when rho is diagonal with equal entries. On the other hand, it vanishes for pure states where rho squared is actually equal to rho. Okay, so in the context of this talk, another important concept will play a role, which is called entanglement entropy. So to briefly tell you what this is, we consider a product Hilbert space H, which is this tensor product space of a Hilbert space A and another Hilbert space B. And so for this product Hilbert space, we can define a reduced density matrix rho A, which is given by taking the total density matrix rho tot and then tracing over all the states in B. And then the entanglement entropy is precisely this von Neumann entropy, which I showed you on the previous slide, this one, but now calculated for this reduced density matrix. And so this entanglement entropy then gives us information about, for instance, the entanglement between different space regions. So we could think of these 2 Hilbert spaces, HA and HB, to be associated to 2 different regions of space, A and B, as shown there. And so the entanglement entropy essentially tells us about the loss of information if we do this tracing over B and look at the region A. So it's an important concept for measuring entanglement in this context. Okay, so this was a very brief review about some concepts of quantum information, which I think most of you will be extremely familiar with. So now let me move to the other side of the 2 concepts I would like to join together, so which are black holes. They have been in the news quite a lot for the reason of lots of interesting discoveries in the last couple of years in context of gravitational waves. And also there's this nice actually photo, which you can see on the top right-hand figure of where you can actually see a photo of a black hole. And so there are certainly gravity objects with remarkable quantum properties. So they're very massive, and because they are so massive, they actually curve the space around them. So that's what you can see in this diagram on the lower right-hand corner. So there you see space-time, and then there's a black hole, where space-time, which is flat everywhere, then at this particular space-time region suddenly has this singularity. Okay, and then of course from this picture you can see exactly what normally happens if you have a black hole. So if you pass the so-called Schwarzschild horizon, then it's impossible to return, and that's why these objects are called black holes. So and this region of or this circle of no return, or this I should say the space of no return, this surface of no return is called the the Schwarzschild radius or Schwarzschild horizon. And so once matter or light passes this Schwarzschild horizon, it is trapped inside the black hole and cannot escape anymore. So at the very bottom, you can see the metric for a black hole. So you see there's this normal dt squared, dz squared, dx squared, dy squared. But now in comparison to Minkowski space, we have this function f in front. And so you can see that something really terrible happens if z becomes equal to zh, because then this function just becomes 0. And then this means the first term in your equation is suddenly 0. And then, of course, something really terrible happens to your space. And there's something really degenerate happening in this scalar product then. And this I can illustrate by this figure here. So we can actually, the structure of black holes is very much related to the causal structure of space-time. Okay. So imagine a light ray. So in this diagram, first in the top line, you see what happens in flat space, and then below you see what happens for a black hole. Okay, maybe I should leave the full screen mouse mode, because then I can show with my mouse. I think that's quite useful in this diagram. So imagine a light ray that travels at the speed of light. So then, of course, this relation is satisfied. And since I'm a relativist, I'm allowed to set the speed of light equal to 1. So then this means that this equation just becomes x is equal to t. So if I draw a diagram of my Minkowski spacetime, then a light ray is going to travel at 45 degrees in this diagram, because it travels at the speed of light, and we satisfy, this relation is satisfied. So the light ray goes in this direction. Now, if an observer is sitting at the origin of the space, given by this space coordinate and this time coordinate, then this observer is influenced by what happened in the past. So that's what is inside this region of the diagram. And she will influence what happens in the future, which is this part of the diagram. However, she cannot influence the physics which is happening there or there, because then signals would have to travel faster than the speed of light. And that's not possible according to the postulates of general relativity. Now, in a black hole, something rather astonishing happens. So this is the structure for Minkowski space-time. Now, for a black hole, if we are very far away from the black hole, so this is actually, let me go back. So this is when we are sitting here, say, then everything is just as I described for flat space. And so this is this so-called causal diamond. So the observer can influence what happens in the future, and is influenced what happens by what happens in the past. Now, but as this observer moves closer to the black hole, so assume she travels in this direction here to here, then the space-time is going to be curved, and then this light cone is actually going to bend. And so you can see that the right-hand side of this light cone starts to move over to being vertical. And then once the observer reaches the horizon, the Schwarzschild horizon, the light cone takes this shape. And then you see that something really terrible happens, because the future is now restricted to this space-time area. So there's actually a singularity here where the curvature becomes infinitely strong. And then the observer cannot escape anymore from this black hole. And that's the origin of this Schwarzschild horizon. Okay, so that's now what I told you so far is essentially about the classical structure of a black hole when you solve Einstein's equation. But now, of course, we are very much interested in the quantum properties. So, and as already Hawking postulated a long time ago, I think in 1977, black holes emit thermal radiation. So they are somehow associated to a temperature. So in Hawking defined this temperature, which is proportional to the inverse of this horizon. And of course, if we have a thermodynamical system and there's a temperature, then there's also going to be an entropy. And in this case, this is going to be the so-called Bekenstein entropy, which you can see written there. And the key factor about this Bekenstein entropy is that the entropy is given by the horizon area. So this AH stands for the area of the horizon, and G is the Newton constant. So it's divided by 4 times the Newton constant. Now, you see that there's something very peculiar about this entropy, because normally entropy is an extensive quantity, so it scales with a volume. But now in this case here, it actually scales with an area. And so this is a kind of semi-classical consideration for black holes, so the Hawking radiation. And of course, if we really wanted to understand the quantum nature of black holes, we would need to understand quantum gravity, which is still a long way away from today's results in theoretical physics. And there's, in particular, there's the so-called black hole information paradox, which tells us that if matter in a pure quantum state enters a black hole, it is transformed into the mixed thermal state. And so this means that information about the original state is lost, and there's a loss of unitarity because something pure becomes something mixed. And to really understand why this happens, we would need a full theory of quantum gravity. However, there's lots of ideas where this information actually goes. And some of them will appear in the next slides. So let's go back to this Bekenstein entropy. So as I said, the key point of black holes is that their entropy scales with their area rather than their volume. And so this is a realization of something rather general in physics, which is called the holographic principle, which means that the information content of black holes is encoded in their horizon area, like in a hologram. So if we look at this picture here of a hyperbolic space, then we see an interior of the space and a boundary. Okay, let me use my mouse again. So this is the interior of the space, and this is the boundary. And then the holographic principle states that the information stored in this volume is actually encoded on this boundary. So this is like a hologram, if, as you have on your banknotes, so where you have a 2-dimensional surface that can be, from which you can reconstruct a 3-dimensional image. And so the information in the two is the same, and that's usually referred to as holography. So, and here also in quantum gravity, this word holography is used in a more general context. Okay, so so my goal is to explain to you what the relation is between a quantum computer and a black hole. And so now we have to take a slight detour, which goes through my area of research, which is gauge gravity duality. So this was originally proposed by the rather famous, extremely famous physicist from Argentina, Juan Mallastina, already in 1997. And for the case of finite temperature that I'm going to talk about as well, this was generalized by Witten in 1998. So originally this goes in the name of ADS-CFT correspondence, where ADS stands for anti-de Sitter space and CFT stands for conformal field theory. So it's a particular hyperbolic space and a particular very symmetric quantum field theory. So now the idea of this correspondence is that black holes in hyperbolic spacetimes are mapped to strongly coupled quantum field theories at finite temperature. Okay, so this is really important to understand. So we have this equivalence between a black hole in a particular curved spacetime and a quantum field theory that has finite temperature, as we normally use, say, for describing many-body physics systems. And like in this black hole I was just discussing before, the information stored in the black hole is mapped to information stored in the quantum field theory on the boundary of the space. And this is a very interesting idea, which I will explain a little more in the next slides. And my research in the last couple of years has in particular been concerned by extending quantum information concepts to infinite dimensional Hilbert spaces. So normally if you talk about a quantum computer, you talk about a few qubits. But here now, if we want to use this map between quantum field theories and gravity, a quantum field theory is always a theory that has an infinite dimensional Hilbert space. So we need to extend these quantum information concepts to infinite dimensional Hilbert space to make full use of this relation that I'm just explaining to you. Okay, so what is gauge-gravity duality? So first of all, what is a duality at all? Well, I mean, this word duality has many, many meanings in mathematics and physics. So I'm using a rather general definition of duality that you can see in this figure. So assume you have one particular physical theory, which, as you know, is given by a Hamiltonian or an action. And this describes a particular physical system that you see at the bottom of this diagram. And then assume you have another theory called theory 2, which is given by a different action and different Hamiltonian, but also written in completely different degrees of freedom. But it turns out that it describes the same physical system. Now that sounds unlikely, but actually is quite common in physics. Now, if you have these two different theories describing the same physics, then they must be related to each other, and this relation will be called a duality. Now, this happens quite frequently in physics, but the very special fact about gauge-gravity duality is that it maps a quantum field theory, or a particular quantum field theory, a gauge theory, to a gravity theory in higher dimensions. And so that's quite revolutionary, because that, if you really take this idea to the end, it might mean that gravity is not something fundamental in nature, but it's just a quantum theory in different disguise. Okay, I'm not sure if I would take this idea so far, but I mean, if you are really pushing it to the limits, that's what this actually implies. Okay, so I should say this proposal is still at the level of a conjecture, and this conjecture follows from a low energy limit of string theory. Let me summarize the two essential concepts which will play a role for us. So on one hand side, this is a duality. So this means a quantum field theory at strong coupling is mapped to a theory of gravitation at weak coupling. And that's actually quite useful, because normally it's very hard to compute anything in a quantum field theory at strong coupling. And now with this method, we can map some problems which are very hard to solve to some other problems that are much easier to solve. I think there's a question. Let me see if I can read the question.
I can read it to you.
Yeah, I have it. Just to be clear, can you specify what do you mean by the term theory? Does it just mean some physical system with a Hamiltonian? Yes, exactly. Okay, so let me go back for one slide. Thanks for this very good question. So yes, okay. By theory, I mean exactly what we mean by this usually in physics. It's a particular Hamiltonian. If you work in quantum body physics in relativity, then you would go to the Lagrangian, and from the Lagrangian you get an action. And so if I talk about a theory, I mean that you really write down H is equal to, and then you put your Hamiltonian there, or correspondingly your Lagrangian. Yeah, so the answer is yes, it's exactly what you have written in your question. Very good. Okay, so on one hand side, we can, if I say a quantum field theory, again, I mean a particular Lagrangian. And then the theory, of course, is quantized, and sometimes, or quite a lot, many times in quantum field theory, you get something as strong coupling, which is where you can't use the standard perturbative approaches, but here we can circumvent this by mapping it to a weakly coupled theory of gravitation. And then the other important concept is the one of some generalized notion of holography based on this holographic principle that I explained to you. So you have a quantum field theory in d dimensions that is mapped to a gravitational theory in d+1 dimensions. And so as in this figure I showed before, you can imagine your quantum field theory as living at the boundary of the space. Okay, so the quantum field theory is defined here at this d-dimensional space, and your gravity theory will be inside in this d+1 dimensional space. Okay, So this is a very short lightning review. So actually, I should say this is really my area of research. So I have written a book about this, and okay, so together with a former student of mine, and so maybe we can take this short commercial break and let me advertise my book. But okay, so I can only be super brief now explaining this, but you know, you can see in here on the title page is already the same picture again with the interior and the boundary and this hyperbolic structure. So I've written this book actually based on a lecture which I gave at LMU for a couple of years, and Martin, my co-author, used to be my PhD student. He did the examples classes for this course, and so he's now a professor himself in Jena actually. And so you know, this book contains everything you want to know about gauge gravity duality. Okay, in particular, in the very last part of the book, there's a statement about entanglement entropy. So now let me continue, and slowly we'll get back to the quantum computers. So a very important development in this subject arose in 2006 by two Japanese authors, Ryo and Takayanagi. And it's actually possible, as they showed, to realize this entanglement entropy, which I mentioned at the beginning of the talk, in this gravity context that I just explained to you using gauge gravity duality. So, and as these two authors proposed, the leading term in the entanglement entropy it will be given by the area of minimal surface in the holographic dimension. So here again, I need to use my mouse. So, so now I've drawn this anti-de Sitter hyperbolic space in a slightly different fashion. So this is the boundary of the space now. Okay, so which in the previous, so here this is the boundary of the space. And now this XY direction will be the direction which goes into the space. And okay, so here we go into this direction into the space. And now I've drawn these two entanglement regions A and B. So B is the complement of A actually in this quantum field theory. So, and now Ryo and Takayanagi proposed that the minimal area surface, so remember this is a hyperbolic space. So there's a minimal surface which you can attach to the circle which you have on the boundary of this space. And then if you calculate the area of this surface, it will give you precisely this entanglement entropy. So here, for the first time, we see a relation between a concept relevant for quantum computing and something related to black holes, because we have a map between a geometrical quantity and a quantity that expresses entanglement. Now, let me be a little more precise about this. So, and let me show you some formulae actually. So, as I said, if you want to have this map, you need to extend the quantum information theory concepts to infinite dimensional Hilbert spaces, because we want to talk about quantum field theories. And so also, as I mentioned, in the simplest example of this gauge gravity duality, which is the ADS-CFT correspondence, the starting point is a conformal field theory in 1+1 dimensions. And for this theory, so it's a particular symmetric quantum field theory. And Cardi and Calabrese actually calculated the entanglement entropy for this theory, which is actually quite an involved calculation given the fact that the Hilbert space is now infinite dimensional. And you see the result is there. So it's S is C/3 log L times lambda. So C is the so-called central charge of this conformal field theory. So it's essentially a number characterizing this very symmetric quantum field theory. L is now the length of a strip that is considered as this region A in our space-time description, and lambda is some cutoff. Okay, and now the interesting thing is that the same result is obtained in this gravity approach using this Ryo-Takayanagi formula. So then we just have to replace the momentum cutoff capital lambda by 1/epsilon, where epsilon is now a space cutoff in the radial direction. So a cutoff in this direction. So we go to some epsilon just here. Okay. And then also there's an identification between the central charge and some geometrical quantities, which you can see there. L is the so-called ADS radius, so it's a radius that characterizes this hyperbolic space. And G3 is the Newton constant in 3 dimensions. So this field theory in 1 + 1 dimensions will be dual in the sense I described to a gravity theory in 3 dimensions. Okay, and so this is very, very interesting because a standard quantum field theory calculation involving the replica trick and so really involved quantum techniques is reproduced by doing a calculation in geometry, in gravity, by calculating the area of this surface. And so it's 2 completely different calculations which nevertheless give exactly the same result. It's also interesting to note that this result can actually be extended to finite temperature. And so the last equation on this slide shows you the result at finite temperature. Okay, so now we talked about entanglement entropy, and this will come back shortly. But before I move on, let me introduce a few more concepts that are relevant in quantum information theory and that play a role in this context of mapping something to gravity. And the first concept which I'm going to mention is the so-called Fisher information metric. So what is this? So this is something which has been proposed a long time ago in information theory, and it's a metric on the space of probability distributions. Okay, so let me use the mouse again. So we have a probability distribution P, which depends on some, so X is the stochastic variable, and these thetas is a set of n external parameters. And then there's a quantity called the spectrum, which is essentially just the logarithm of this probability distribution. So, and the Fisher metric was proposed a long time ago as being the expectation value of the derivatives of the spectrum with respect to the components of this set of external parameters which are encompassed in this vector. So exactly we can write this in probabilistic notation like this. And now there's a very interesting fact, which is that if you calculate this Fisher metric for a Gaussian distribution, as shown here, okay, so this is a standard Gaussian distribution. So sigma is the standard deviation, and then you see variations around some particular point. And if you take this probability distribution and you plug it into this formula, then you get a metric of this hyperbolic anti-de Sitter space, where this radial direction actually corresponds to the standard deviation in your distribution. And so that's a remarkable fact. So you start with a Gaussian distribution, and this gives you this anti-de Sitter space. So then you would say, okay, this is actually almost exactly what I told you before. However, there are some caveats because the problem is that this procedure doesn't tell us anything about the dynamics in the space. But really to understand this duality and the quantum gravity side of things, we would need to how the dynamics arises in this gravity theory. And for this, this information is just a beginning, but it's not really the end. But nevertheless, this is also another interesting concept which plays a role in this game. And if you're interested in more details about this, there's this recent paper from January of this year, which I recommend to you. Another question. What does it mean for a probability distribution to have external parameters? Well, okay, so I guess in the case of this Gaussian here, you could, for instance, these x's would be external parameters if you just say you want to fix where exactly your Gaussian, the center of your Gaussian distribution is fixed. Okay, so then you have these x bars. So these x's, they give you the location of the maximum of your Gaussian. So this I would consider an external parameter of the distribution. Okay, so okay, sorry, there was some other comment, but I don't think there was another question. Okay, I hope this answered the question. Okay, so yet another important context which is usually used for describing quantum computers. So if you have a quantum computer, you would like to somehow measure their efficiency in some way. Or to put it in a different way, you would like to understand how complex the input and output of the result of your calculation are. So, so the complexity in quantum computing is usually defined in the following way. So you consider a set of predefined unitary transformations in the Hilbert space. So imagine your quantum computer is made out of somehow 10 qubits, 10 spins, entangled spins. And then you define some operations which would correspond to actually flip these spins. Okay, so in a certain way, say you have 10 of these qubits, and one operation you flip 5 of them, and another operation you've flipped 3 different ones. And so this way you could define your unitary transformations. And then if you have this set of finite operations that are allowed, then the question is how many of these need to be applied to reach any given state in your Hilbert space from a reference state. So the reference state is the input of your calculation, and then you have to apply these transformations. And if you want to get to a state which is very far away from this, then of course you need to apply many of these. And so this would give you a measure for the complexity of a calculation. How many operations do you need to apply to your first state to get to some final state? So, and now if you look at the second half of the slide, I explain this in much more technical terms. So consider a reference state R in a Hilbert space and a set of unitary operators, U1 and U2 and so on, which are usually referred to as the gates. And then the complexity C of a state psi is given by the minimal number of gates required to map R to psi up to a given tolerance. Okay, so that you can see in the very last line there. So we apply these unitary operators U to R, and you just count how many of them you have to apply. Okay, now I want to show you that you can actually, so this is a concept which is very directly related to quantum computing. And very recently, people have proposed that the same concept plays an important role to describe describing black holes. And so this is where I want to take you next. Okay, why could this? I mean, here you see it's really a computational thing that's defined for quantum computers. How could this be of any role for describing a black hole? Okay, so this is the goal of the next few slides to answer this question. Okay, so in order to answer this question, I have to introduce another concept in a more kind of many-body theoretic framework, which is the so-called thermophile double state. And this you can see here. Okay, what's a thermophile double state? So we begin with a vacuum expectation value in quantum mechanics, which you see on the first line. So you see this expectation value as just by sandwiching an operator A in the vacuum state. Now, imagine that you are doing quantum statistics at finite temperature, and then of course you have an expectation value of this observable at a finite temperature, which is given in the second line. And so there you have to take the trace of rho A, where rho is the density matrix, and normalize then by I would say the partition function. Okay, so yeah, I think it's called partition function or generating functional in quantum field theory. Okay. Now the idea would be to write a VEV as before, so a vacuum expectation value for this finite temperature situation. And unfortunately, for this, we have to actually proceed via a slight detour, because to really have a vacuum expectation value at finite temperature, we actually need 2 copies of the original Hilbert space. So instead of looking just at the Hilbert state one time, we tensor product this Hilbert space with itself and get a new Hilbert space called H, which is, so H1 and H2 are the same. Okay, this is 2 copies of the same Hilbert space. And if we do this doubling, so that's why it's called double state, and also then it's actually possible to write a thermal vacuum state in a complete basis. And so the state will be called 0, 0, beta. So beta is the inverse temperature. And then the vacuum, we have the vacuum and a copy of the vacuum because we have this copy of our Hilbert space. And then, well, you can see the calculation there, how this can be expanded in the states in this double Hilbert space. And then now instead of the operator A, which was considered on the first line, now we consider this operator curly A, which is a tensor product with just the unit operator. And then if we calculate the thermal expectation value, then we can actually define a vacuum expectation value, which is of the same form as in the first line. And okay, so this doubling is absolutely necessary for having a vacuum expectation value at finite temperature. And so the state, which is now a new vacuum, is this thermophile double state, which is in this red box. Okay, and now, so before I just wrote these probability distributions in terms of this functions f, but of course, f now is given by this Boltzmann factor, which you see at the end of this equation. So now we can expand this vacuum, double field vacuum in terms of the Boltzmann factor and the eigenstates, as you can see in this red box. So this is now what is our thermophile double state. And this has two interesting limits. One is if you take the temperature to infinity, then you get a pure maximally entangled state. And on the other hand, if you take the temperature to 0, then the quantum mechanical vacuum expectation value in just one Hilbert space is recovered. Okay, so there's a certain trick of doing this doubling of the Hilbert space in such a way that you get an expectation value, a vacuum expectation value at finite temperature. Okay, so as you will see shortly, this thermophile double state has an important relation, significance if we want to make a connection to gravity. And this now actually comes in the context of the so-called ER is equal to EPR proposal, which is due to Susskind and Madasena from 2013. And so they suggested that an Einstein-Rosen bridge, which is actually a wormhole, which you can see there in this picture, is actually corresponds to a maximally entangled state, as you can see on the right-hand side of this graph. Okay, so now I need my mouse again. So, and now here the thermophile double state plays an important role. Now let me explain this diagram. So this is a so-called conformal diagram, which is often used in general relativity. And this is now a plot of this black hole in an anti-de Sitter space. And let me explain what you see in this figure. So first of all, this is, again, there's a coordinate system and time goes in this direction. And the radial coordinate of this anti-de Sitter space goes in that direction. Okay, so this is our just time and space coordinate. Oops. And now if we have a black hole, there's actually going to be a horizon. Okay. So this line here is the horizon. So imagine, so your quantum field theory will be located at the boundary of this anti-de Sitter space, so which in this figure now is here. And then if you propagate inside the radial direction, this will be in this direction now. And then at some point, again, we will hit this Schwarzschild horizon here. And now, if we depict this anti-de Sitter space in so-called global coordinates, it actually turns out that there's a copy. So if I say the word copy, it should ring lots of bells now, because I was just talking about this thermophile double state. So there's a copy of this on the other side. So here there's another quantum field theory, which is defined on this side. And there you can propagate here until you hit the horizons again. And so then you see that essentially we have a picture of a wormhole, okay, because one can, in principle, well, I mean, it's a so-called non-traversable wormhole. I mean, you can just go in this direction, but you cannot come back on the other side. But what so it is definitely a wormhole because there's two exits to this black hole region here in the middle. So essentially this side is here and that side is there. Okay. And so now you can define a state in your quantum field theory on this side and another state in your quantum field theory on that side. And then they can be linked by a geodesic. So these lines correspond to geodesics at different times. And then essentially this proposal now tells you that if you have two thermophile double state where one of the Hilbert spaces is here and the other Hilbert space is there, then in this picture they will be linked by such a geodesic going through this wormhole. Okay, so let's go back to our thermophile double state. So we have two Hilbert spaces, and then we have this entangled state between these two. And then now in this figure, you can imagine that one Hilbert space is here and the other Hilbert space is there. And the two parts of the space are entangled and this entanglement in the gravity picture is then depicted by these lines which go through this wormhole region. So yeah, question. Can the two entangled states be swapped? Okay, I don't. Well, okay, so one has to be a little careful. I don't think so, because the problem is that if you go from here to there, in principle, you would need to go backwards in time at some moment. Okay, so that's why it's called a non-traversable wormhole. And so I'm not quite sure if this is possibly, of course, just formally, I'm sure you can do a coordinate transformation where you go from one side to the other. Yeah, I mean, the thing is, it's a symmetric problem. I mean, I'm sure there's a coordinate transformation where you can swap the two, this for sure. But if you actually think of taking one side to the other, this is a more complicated story. And yeah, I mean, if you want to respect causality, oh no, there are lots of questions. Okay. Well, that's just the thing. It cannot. Okay. Very good question. Okay. So the question is, how can the geodesic go out of the black hole again after crossing the horizon? And the answer, well, okay, I was sloppy in talking. It cannot. Okay, so you can start on this side and go in this direction, and you can start on that side and go in that direction, and then meet in the middle. But once you got in from this side, you cannot go out on the other side. Yeah. So thanks for this clarification. So I shouldn't say that. You can start here and go there, and you can start here and go there and meet in the middle, but you cannot just leave the black hole again. Yes, sorry for sloppy language. Yeah, very good question. Okay. Okay, so actually now there have been quite a lot of suggestions how to implement this concept of complexity, which we just discussed before for quantum computers in the context of black holes in holography. And here I'm going to refer to this paper by Susskind from 2016, the two papers. And again, we consider the evolution of two copies of a conformal field theory, which are initially entangled in such a thermophile double state. So on the left, again, you can see the same diagram as I was just discussing. And so there's this issue of complexity, which I defined to you. Maybe I should go back to just show again. Yeah, okay. So complexity in quantum computing is the question, how many of predefined unitary transformations do we need to be applied to reach any given state from a reference state? And so now the idea of Susskind and collaborators was that you can ask a similar question for black holes. That's shown here on the left-hand side of this diagram. So Susskind now suggested the following. He said a measure for this complexity in this gravity context would just be the length of this geodesic. that joins these two regions of space-time. And this is a proposal, and there's been quite a lot of work of actually understanding this proposal and mapping it to something in quantum field theory. There's another proposal where just considering the length of this geodesics, which if you generalize it to higher dimension would be the volume of this bridge. Here the other suggestion is to calculate the action in gravitational action in a particular causal region of space-time. So that's shown in this diagram here. So this is a different proposal, again associating a geometric or dynamical object for a black hole to some concept of quantum information theory, which in this case is the complexity. Okay. So now why should, I mean, this is really a suggestion, and there's now currently quite a lot of work of actually making this map precise. And there's been quite a lot of results now for free quantum field theories, but for interacting quantum field theories, it's still an open question. And so the initial motivation is, so why should this geometric objects have anything to do with this complexity from quantum information? Well, the reason, one reason given in these papers is that both these proposals, this volume and actual proposal, they both evolve linearly with time. And in quantum computing, it actually turns out that every step in the calculation is associated to a fixed time step. Okay, so the more you compute, the longer it takes, okay, because every step takes a particular amount delta t of time, okay? And this is always the same, and so complexity grows linearly with time, and this is also the case for these gravity proposals here. And then there's an interesting fact that black holes actually saturate the so-called Lloyd bonds. So Lloyd is this very famous quantum computation physicist. And so the time change of the complexity is actually bounded by the energy of the black hole. For the black hole, its energy is actually corresponds to its mass. So the statement of this bound is that now actually the black hole can be viewed as a very fast computer. Because the change in complexity is smaller than the energy, which is associated to the mass of the black hole. And there's a very nice discussion of this in this paper, which I have given here, which I very much recommend in this context. Okay, so it's very interesting to see that you can map these gravity and quantum computation concepts again. Okay. So I'm almost at the end. So I should ask, so how many minutes do I have left?
It's fine. We have plans for breaks and so on. You're okay.
Okay. So okay, let me not go for too long. I mean,
I mean, within reason, I think.
Yeah. Okay. I think I need another 5 minutes. Okay. Good. So, so I'm almost at the end of this part of the talk. So, which okay. So I showed you this very nice connection between quantum computing concepts and black hole and gravity concepts. And so now this actually leads me now to a project that we are doing inside our Exynos cluster, CTQMAT. And so because we have these two hubs, so we are partially in Würzburg, partially in Dresden, we are very much encouraged to have joint projects with people from both sides. And so here I'm showing you this work in progress with our colleagues in Dresden. And so they are at the Institute für Werkstoffwissenschaften, so really a lot more applied than what my actual background is. And so the idea is that we are pursuing right now is, okay, so far I showed you this relation between quantum computing and geometry in this rather complicated thermofield double setting. And so, of course, if we would like to go closer to experiment or deduce some facts that are really relevant for, I only talked about quantum computing in this very idealized way, but of course there's lots and lots of technical problems like decoherence, interaction with the environment, and there's always this question: how do you do the measurement process? And these are important questions for quantum computing, and I didn't touch about this at all. And so the idea that we have now for this project within the cluster is that we say, okay, now we have this very beautiful geometric structure. Can this be of any use for constructing something which in real world quantum computing is leads to some very stable states, for instance? And so the plan is to study geometric structure of entanglement in much more simple systems than these sum-of-field double state, for instance. And so the very simplest thing you can think of is two interacting spins that are entangled with each other. So this is a system which we started with because we wanted to really do something simple. And so at the moment we are developing a path integral formalism for entangled states to actually study precisely the geometry that is associated with this with this entanglement structure. And of course, this will not be a wormhole. I mean, for this, the system is far too simple. But certainly, we can just determine what the geometric structure is and in what sense it is very different from a wormhole. So this is a rather, I wouldn't say applied, but much more down-to-earth quantum matter related topic than anything I was saying before. But it's very nice to see that people from my background can actually collaborate with people in quantum science for very basic or practical questions. Okay, so I have a list. So I told you lots about concepts, so I didn't tell you very much about my own work. Okay, so now since time is almost up, I won't say very much. So here's a list of recent things that we did, and let me not go through it, except I would like to point out the two papers with my female PhD students. So this paper is with my former student Nina Miklai, so this is an all-female paper. Okay, it only has two authors. Okay, fine. And my current other student is Annalena, and she's also very much involved in these complexity issues. So, so again, if you want to know about all these other things that we've been doing, then just ask me. Okay, so I was going to tell you about this recent paper, and I should really keep it very brief. The only thing I would really like to tell you is that we have another topic in this context of gauge gravity duality in the context of the cluster, where we again make use of these very kind of abstract general concepts involving gravity and really make a connection to condensed matter and quantum materials. And so I would like just to mention this a very nice paper which we wrote together with our colleagues from condensed matter here in Würzburg. So this is the group of Ronny Tomane, with which we collaborated. So this is a mixture of quantum field theorist, string theorist, and condensed matter physicist. And this actually appeared in Nature Communications this summer, so it's a very nice result of this collaboration. And so the paper deals with turbulent hydrodynamics and strongly correlated cargo-mean materials. Okay, so cargo-mean materials are particular strongly coupled systems in condensed matter physics. And so now what we advocate is that you can actually discover some hydrodynamic behavior of the electrons there, and even maybe some turbulence. Okay, so since I'm really out of time, I probably won't tell you any details, but let me just go through this rather briefly. So I should say at the beginning that gauge gravity duality is also useful for calculating transport coefficients for strongly correlated systems. And the most famous example, which has been confirmed experimentally, for instance, for the quark-gluon plasma, so in nuclear physics, is this ratio of shear viscosity over entropy density. And so in this paper, which I'm just mentioning, we have a proposal for a new Dirac material with strong electron-electron correlation in view of realizing hydrodynamic behavior described by gauge gravity duality. And so the question is, can you use hydrodynamics to describe the flow of electrons in a wire? And of course, this is only possible in very small parameter regimes because there's always interactions with the wall of the wire and the impurities and so on. But there's particular regimes given by this. So LEE is the correlation length of the electrons, and if this is the shortest scale in your problem, then this is actually possible. And so here you see a wire. Okay, here you see a wire, and you see the velocity profile of this fluid. And okay, so the question is now to calculate the electron-electron coupling strength, and the bigger this is, the more chance there is to get this hydrodynamic behavior. And okay, so in this paper, what we did, so this was studied quite a lot for graphene, but now in this paper we propose a new material where this should be, these effects should be 3 times more pronounced than in graphene. So here is a discussion of hydrodynamics. Let me skip this for now. So the key point is that these hydrodynamic coefficients, especially the shear viscosity, can be very simply calculated from gauge-gravity duality. Then again, you see my black hole, and you can use it for defining retarded and advanced Green's functions, which are very useful in quantum matter physics. And so then here there's an explanation of how to calculate the shear viscosity. And okay, so the issue is that this is the result, which is this famous result which has been around for quite some time. And you have this very small number here, 1/4 pi. And it's very universal because it doesn't depend on any coupling effects. But so this result is only very valid at very, very large couplings, so infinite coupling. And so if we want to compare to condensed matter physics, we have to look at corrections in the inverse coupling. Okay, so here this is explained how this is done. So in gravity, we use propagation by using this Einstein-Hilbert action in 1 dimension higher. And sorry. And then the idea is that we suggest this particular material where all these nice effects that we get from holography can actually be realized in the real world. And so these are these materials with this particular hexagonal structure that you see nicely in this diagram. So our idea is based on a particular material which you can see here, which is called Hilbert-Smithite. So this is a material which obviously exists because there's a picture of it in Wikipedia. Okay. But now what we need is a so-called Dirac material where the Fermi surface has to be precisely at this Dirac point in the band structure. Okay, so our Fermi surface has to sit there. But in this Hilbert-Smithite, it's actually there. And so what we suggest is to replace the zinc atoms which are in this material, or zinc ions which are twice positive, by scandium with a 3 times positive, and that will shift the Fermi surface from here to precisely this point. And then we will get a material which has a nice relativistic dispersion relation and this very strong coupling. So, and then there's a great chance that all these hydrodynamic effects will be much more pronounced. And so here you see this Dirac cone. So the black line is the Dirac cone of graphene, and you see our cone is much wider. And this means that this effective coupling will become much larger. Okay. So
I would suggest something like 2 more minutes, maybe.
Yes, I have exactly 1 more slide. Okay, sorry. Yeah. And then, what we did in this particular paper is that, so this red line is this 1/4 pi, this value which was already calculated, and now we study from holography the coupling corrections. And so there's a certain uncertainty, but we suggest a particular band. And then we see that this new material has a very much, so this is the coupling strength and this is the shear viscosity. And so with this new material, we would be at a much better value of the coupling to investigate these holographic effects than in graphene. Okay, so that's all I wanted to say. So I should thank my past and present members of our team here in Würzburg. And okay, so this is the conclusion. So the conclusion is very short. So gauge-gravity duality is a new paradigm in physics. I showed you in the major part of the talk, it provides new relations between entanglement and space-time. And at the very end, very briefly, it showed also new methods for, I showed also new methods for strongly correlated systems, which are extremely useful. And then sorry for taking so long, and I'm done.
Thank you very much. I think there's a lot of input, and I think it would be, we will have the Q&A where everyone is invited to join in the round table. So that's a Zoom meeting, so we can kind of interact better. So I would say take 3 minutes. So we meet at 43 again in the round table.
So what do we have to do to get there?
Just switch. Just take your click on the Meet Anyway template. Click on the round table and join on the join button, and you will be there. It doesn't work right now because I'm in this meeting and I have to open the other meeting, but it will work in 3 minutes.
Sorry, so I go to this web page and then click join. Okay, I think somebody raised his hand. Yeah, there's a raised hand. Maybe we should answer this first.
Okay.
Yeah.
Yeah.
Yes, thank you first for the very nice introduction and overview to this topic area. I'd have a question, which is about, so space-time in our universe, as far as I know, does not have any negative curvature, but the A part in the ADS, the hyperbolicity, seems to be rather important. So for example, in the Roy-Tagayanaki formula, I think if you would have positive curvature, then somehow it seems that the minimal surface would not actually extend into the bulk, but just go around the boundary. So
okay, should I answer no? No, should we?
How it relates to our space-time universe, or what the relation is?
Yeah, I'm very happy to answer the question, but I understood we should first go to this other.
I would. Is it okay if we take 2 minutes break and meet in the meeting? Or,
but I would certainly be very happy to answer your question. So hello.
But we can also, okay, we answer this question and then.
I'm sorry, I just thought that the roundtable was for female.
Yeah, no, but we would open it for 10 minutes and then.
Okay, sure, then I can wait.
No, okay, but let me answer the question. Okay, hello, thanks for joining. Actually, I'm familiar with your work. I read this recent paper, which we had, I think, last year. Yeah, so I'm very happy that you joined. I think what you did last year was also a very interesting paper, and it's actually quite related to what I was talking about. So to answer very quickly, yes. I mean, okay, so everything I talked about in gauge gravity duality, as you correctly say, is for black holes which are in this hyperbolic space, of which I had many pictures. And you are completely right. I mean, our universe has if it has a cosmological constant, this will be positive and not negative. So this space is not the universe. This space is not the universe. Okay, it's, if you want, it's a mathematical space which allows you to study quantum properties of black holes in a simpler setting. And okay, due to the symmetries of the spaces and due to this holographic principle, it is much easier to study quantum properties of black holes in this very symmetric case. But you are absolutely right, and I totally agree that this has nothing to do with our real world. Okay, but nevertheless, you can use this as a tool for a better understanding of some simple version of black holes, and also you can actually use the duality to make statements about the dual field theory, which is also very interesting. So that's the first thing I would like to say, but I should also say that recently there has been quite some attempts by people to construct also other versions of holography. There's something which goes under the name of flat space holography. For instance, there's somebody called Daniel Grumiller in Vienna who's working on this. And so where people try to extend this to black holes which are inside a flat space. It doesn't work so easily because you have a lot less symmetry. And the good thing about this anti-de Sitter, this hyperbolic space, is that the symmetries match with the symmetries in the field theory, and then you know exactly what you are talking about. And if you get rid of this hyperbolicity, then things become a little more up in the air and you have less control. Okay. But nevertheless, people are also working on that. So if you are interested in this, I suggest looking at these papers. it's an open problem, but nevertheless, what we have so far is certainly very useful to get some information about entangled quantum systems, even if the space is a little academical and has nothing to do with the real world.